Hey y'all, Dr. B here. Today we're going to be talking about polynomial functions and their graphs. As I was doing this lesson, I realized I need to make a video on the different, like the basic graphs of the basic functions so y'all can see what they look like. Because when you know the basic graph, you can kind of graph anything. But for this particular lesson here, we are going to go through polynomial functions in the graph. We're going to talk about how to identify a polynomial function, graph characteristics, the end behaviors of the graphs, zeros, multiplicities of zeros. Y'all are probably like, what does that even mean? The existence of real zeros, turning points, and of course, common mistake and key takeaways. Basically, what we're going to talk about is how to graph a polynomial function, whether it's a linear function, a quadratic function, a cubic function, and then any polynomial function above that. That's essentially what we're going to do. And the reason why you have topics like these, because can you do t-tables? Can you point x-intercepts, y-intercept? Yes. But these, if you want to call them not tricks, but if you want to call them like tools, they kind of make it easier to know, okay, what does my graph even look like? And then that gives you an idea of how to graph it. So it kind of saves you time. So let's get started. All right. So how to identify polynomial functions. So here's the definition, and then I'm going to try to put it in Dr. B language. Let n be a non-negative integer, and let a sub n, let a sub n minus 1, a sub 2, a sub 1, a sub 0 be real numbers, where a sub n is not equal to 0. That is the definition of a polynomial function. Basically, or this is the beginning of it. Let me say the beginning of it. But before I even jump in to show you what they look like, because you've seen them before, I want to make sure you know what real numbers are. So you look at this block right here. These represent real numbers. So this, if you think of this as this is your real numbers, this is the whole world. So you have irrational numbers over here, and then you have your rational numbers over here. But both of these sides here make up real numbers. And you're probably like, well, Dr. B, why does it matter? Because in math you have imaginary numbers. Yeah. You have you're gonna have some imaginary numbers, so you have real numbers. So on this side, these are just your irrational numbers, like e, pi, square root of 2. Okay, these are going to be like numbers that don't repeat, go on forever. They're irrational. They're just doing the most. So if you think of numbers that do the most, besides imaginary numbers, it's these irrational numbers. The irrational. Now, your rational numbers are numbers that you're used to. Like, for example, your counting numbers. Counting numbers, when you learn to count, 1, 2, 3, 4, 5, 6, 7. Natural, I think sometimes they call them natural, but you're counting numbers, okay? And then from counting numbers, you jump to whole numbers, where whole numbers are just 0. 1, 2, 3, 4, 5, 6. So the only difference between your counting numbers and your whole numbers is going to be now you've incorporated 0. And then you jump into integers. Now notice counting numbers is small, and then whole numbers includes your counting numbers, and then integers includes whole numbers and counting numbers. So when they say real numbers, they mean anything in this box here, okay? Most of the time you're going to see numbers that are over here that are rational. And when they say non-negative, they mean positive. So where your n's are positive, and then your integers, let me give you those. So -1, -2, -3, 0, 1, 2, 3. The numbers that you would see on a number line. Now, integers would also include, like if you had 4 over 2, because that's really 2. So that would really include your integers. So it's your positive and negative numbers. And then when you're talking about fractions and decimals, those are going to be your rational numbers. But all of these kind of fall under the rational numbers, and then just know the irrational numbers are going to be the ones that don't repeat. They go on forever and ever. You don't know when they stop. They're totally irrational. So just remember that. And then imaginary numbers, but we won't cover that here. So here's the rest of the definition of how to identify polynomial functions. So if you have n, that's a non-negative integer, meaning it's a positive integer, and all of these constants represent real numbers. They're real numbers. They're not imaginary numbers. They're real numbers. And this first a sub n is not equal to 0, then this is what the polynomial function looks like, just like that. Okay, you have f of x. Remember, when you're talking about functions, you use f of x, but when you're talking about equations, you use y, okay? So y is the same thing as f of x, is essentially what I'm saying. Y and f of x. Y if you're talking about equations, f of x if you're talking about functions. So they represent the same thing, okay? Don't think anything different. And then x is the same on either side. So this is what it looks like. You have your coefficient that's tied to a term, and then your term has a non-negative integer as a power. The number that's in front here, that's on the term, that's attached to the variable with the highest power, that is called your leading coefficient. That's leading everything, okay? Now, you're probably looking at this and you're like, this don't look like nothing I've seen before. Let me show you some examples, okay? So here are some examples of polynomial functions. And if I go back to this definition, I want you to pay attention that the exponent is not negative. Okay, it's a positive exponent. And then I also want you to pay attention that the leading term and the leading coefficient is not 0. The leading term is at the beginning. And the leading term is attached to the variable with the highest power, the largest exponent, okay? So let's look at this first one. Or let's look at all of these, really, and we're just going to go through them. So x squared plus 14x plus 45. This is a polynomial function. Why? Because each coefficient that's attached to the variable, it's a real number, and the exponents that are on the variables are non-negative. Okay, you don't have any fractional, you don't have like 1/2 or anything like that up there. So this makes it a polynomial function, okay? It has a leading coefficient of 1. Now remember, you don't write the 1. It's understood 1, and anything higher than 1, you write. And then the degree of a polynomial function, did I have that on the last page? Let me see. I did not. The degree of a polynomial function is the exponent on the largest term, okay? So this says x squared, right? This says x squared, this just says x, and this doesn't have it. This has a degree of 2 because this is the largest power on the variable. That's how you want to see that. It's the largest power on the variable. Let's look at this second one. This second one has a leading coefficient of -3. You see that? It's the leading coefficient of -3 because this is the largest term, if you want to call it that. This has an x squared. That does not have an x tied to it. So this is the largest term because the 5 is the biggest. So this polynomial function has a degree of 5, and real numbers are okay. This is a real number. And you're like, well, Dr. Anderson, you said it's irrational. The square root of 2 is irrational. But remember, that entire rectangle represented your real numbers. It's not an imaginary number. It is a real number. It just happens to be an irrational real number. So, but this still works, okay? What about this one? This one has a leading coefficient of -1. Now, how many of y'all said 18? If I were to write this in order, it would be -x to the 6 minus 3x to the 5th, right? Plus 18x to the 4th. If I were to write it in descending power order. Now when you look at it, this is the largest power, x to the 6. So that's why it has a degree of 6. So anytime they write it in different ways, which you'll see these terms written in different ways, pay attention to what the largest term is, okay? That has the largest variable, the largest exponent on the variable, which is x to the 6. And then write in descending power order. Okay, let's look at this next one. Is this a polynomial function? Good, it's not. Why? Why? Because there's a fraction in the exponent. Remember, your exponent has to be non-negative integers. Integers are positive and negative numbers, not the fractions, not the decimals. So that's why this is not. So no fractions, okay? No fractions in the exponents, okay? So that is not a polynomial function. Okay, let's look at this next one. Why isn't this one not a polynomial function? Remember, the definition said that all of our powers had to be non-negative. Okay, we want these to be non-negative integers. The powers on the variables, they need to be non-negative integers. Easy peasy. Okay, so this is what they look like. And what I'm going to do, we're just going to go through and say, okay, how do they look? How do you do the graph? What's the end behavior? All of that, and it's totally going to make sense. So let's keep going. Graph characteristics of polynomial functions. So you're very familiar with linear functions, which are the straight lines. Those will have a degree of 1. So if you look at the x, notice that the exponent, remember these are understood ones, you don't write them, so they have a degree of 1. Other polynomial functions that have a degree of 2 or higher, those are going to be like your x squareds and your x cubes. They're going to be smooth. It says rounded curves, no sharp edges, continuous. What they mean by continuous is if you put your pencil down and you start, you can draw it without picking your pencil up. So that's another way that you can tell. Same thing here. If I put my pencil on here and I trace this, you can draw the entire graph without picking up your pencil. So that's how you also, the way that you know that it's a polynomial function. So it won't have any breaks. It won't have any, splits in between it. You'll be able to draw it. Now, some of these polynomial functions get really weird where you don't know how far up they go or how far up they down. But just know the idea is it's going to be smooth. It's going to have rounded curves, no sharp edges, and continuous. I gave you f of x equals x squared and f of x equals x cubed because I want you to get used to memorizing that x squared is the parabola and then x cubed almost looks like an S. And then the higher up you go, you're going to notice that the even ones, where they have an even degree, they're going to be either up or down. And then when they have an odd degree, the ends are going to go opposite each other. Okay? That's what I want you to remember as we go through this. And that's why I'm going to do a video on the graphs of the basic functions so you can see what does x squared looks like, what does x cubed look like, what is x, the graph of x looks like, what is the graph of the absolute value of x, the square root of x. Like, I want you to get those in your mind, start to get those memorized so that when you see them, you automatically know what the graph is going to look like. So the end behaviors, this is what I was talking about. So the end behavior, what I'm talking about, the end behavior are the ends of the graph. What are the ends of the graph doing? Are they going up like this? Are they going down here and then up here? The end behavior. How does the end pieces of the graph act? So the behavior of the graph, the far left, the far right, and then with polynomial functions, they can have many intervals, especially if it's a polynomial function of degree 2 or higher. Okay, so it can really get some waves going. So it says that the graph eventually rises or falls without bound, meaning it doesn't stop. Without bound means negative infinity to infinity. Okay, that means it can keep going up and up and up and up and up. It can keep going down and down and down, but in the middle, it might do something like this in the middle. So that's what they mean. That's what they mean. And it depends on the leading term. So remember, the leading term is the term that has the variable with the highest power exponent, okay? And they have what they call the leading coefficient test. These next couple of slides, I'm going to give you different things that help you know how to graph these functions. But again, I want to reiterate, as long as you have an idea of what x squared looks like, of what x cubed looks like, you're going to be able to graph these other functions. So the leading coefficient test, you use the leading term of the polynomial function so that you know what the graph is going to look like. So if a sub n, if the leading coefficient is positive, if the leading coefficient, or let me see. Let's start here. Okay, let's do this row. And see, I have n is odd, n is even. I'm talking about this n, okay? So whether you have x squared or you have x cubed. Matter of fact, I'm going to fill those in as my examples. So like this will be, let me use white. So x cubed, and see how the n is positive, the 3 is positive. if that happens, if your n is odd, then your graph is going to look like, it's going to look like this. Okay, if n equals odd. So basically what happens, the n behavior is going to go down one side, and on the other side it's going to go up. Okay, that's the n behavior of the graph. You don't necessarily know what it's going to do in between, because x to the 5th, x to the 7th, x to the 9th, all those odd powers, but it's going to be, the n behavior is going to go down and then up. Let me rewrite that. Okay, down and up in x cubed. Now, if it's something like x squared, and I'll put x squared. X squared, if you remember, it looks like a parabola. Then the n behaviors of the graph is going to be up and then up, okay? Up and up. Both ends of the graph are going to go up. That's the n behavior. And so that's why you use this, the leading term, and then look at the degree and then look at the number, okay? So you look at the degree to say, is n even or is it odd, okay? And then you look at the leading coefficient. Remember, a sub n is the leading coefficient, and if it's greater than 0, you got, depending on if it's odd, and then depending on if it's even. Now, what happens when it's less than? So if it's negative x cubed, because remember, your n can't be negative, but your coefficients can. So our degree is 3. It's odd, but our coefficient, our leading coefficient, if it's negative, then it's going to flip-flop. So if it's negative, the n behavior on the left side of the graph is going to go up, and the n behavior on the right side of the graph is going to go down. Okay, so it's going to be opposite. And then same thing over here. If you had negative x squared, it's going to look like that. The parabola is going to flip, so these go the opposite direction. So again, I'm going to stress the importance. Know what x squared looks like, know what x cubed looks like, and then the negative version of that is just going to be the opposite, okay? It'll take time, but if you can remember what these graphs look like, I'm telling you, it's going to save you so much time, so much time. So let's look at these. And this is what I was just showing you, okay? So if the degree is always going to be positive, but if the degree is odd or even, so if it's odd, the n behaviors will always be opposite each other. One will go up, one will go down, or vice versa. One will go down, one will go up. I'd say down and up, right. Okay, y'all know what I'm talking about. But if it's even, the n behaviors of the graph are going to be the same direction, either both up or both down. That's using the degree, okay? Now, when you look at the leading coefficient, remember the leading coefficient is tied to the variable that has the highest power. The leading coefficient, if it is less than or greater than 0, that way, x squared this way. And then when it's less than 0, flip it, and then x squared is going to go down. Okay, so let's look at some. X cubed, see, it goes up. So my n behavior is this way and this way. And then if you can remember, if you memorize that that's x cubed, when you see a negative x cubed, you're going to know, oh, it's going to go the opposite, the opposite directions, where this side is up and this side is down. On this one, this side was down and this side was up. So you see how they just flip directions? That's what you want to know. Some people are like, oh, well, this is really going up and this is really going up, but think of the n behavior. Look at the direction of the n behaviors, okay? Up and then down. So they flip-flop, okay? Now let's look at x squared. Same thing here. The n behaviors, when it's even, they go up. And then when you flip it, they go down. See that? They go down. So you got down, down when it's negative, and then up, up. But that's when you have an even degree. Okay, that's when you have an even degree, same direction, okay? And then when you have an odd degree, opposite directions. I hope this is making sense, okay? Let's do some. All right. The n behavior. What is the leading term? What is the leading term? Good. Negative x to the fourth is the leading term. So we have negative x to the fourth. What is the leading coefficient? Remember, the leading coefficient is the number that's tied to the leading term. Well, we don't write the 1, but it's going to be negative 1. What is the n? The n is the degree. The degree of this polynomial function is 4. So then what's the n behavior going to be? It's an even degree. So I'm going to put this as even. So we know it's either going to be like this or it's going to be like this. The n behaviors, right? Because they're even. Matter of fact, I don't want you to always think parabola. So it's either going to be like this or it's going to be like this. What determines that? Good, the leading coefficient. So we know because the degree is even, we know it's going to be that. Now you have to determine which direction. Well, because it's an even function, I want to think of y equals x squared because that's, or f of x equals x squared, because that's my foundational graph, right? So if I know this goes up, I know the negative version is going to go which way? Down, right? Very good. So this is going to be down and this is going to be down. Remember, at any point you can leave a question. So let's look and see if we got it right. Good. -4, -1, and 4, and the behavior goes down. This right here is, I gave you an example of what the graph looks like. So remember I told you in between, it can do some willy ups and downs, but you care about the end behavior. And that's what I'm saying. If you can learn how these work, how the basics work, then you can figure out what graph I'm looking at. Now you notice it's not exactly smooth like a parabola like that, but it's an even what do you call it? It has an even degree, so it's going to be similar to like a parabola. And you know it's a polynomial function because I can draw it from top to bottom without picking up my pencil. Cool beans? Okay, let's do another one. Look at this one. What is the leading term? It's the largest one, right? Good. So x cubed. What is the leading coefficient? The leading coefficient is the number tied to the leading term. It's a 1 because remember we don't write a 1. It's an understood 1. Anything other than 1 we write it. What is the n? The n is the degree of the polynomial function. It's going to be 3. Now, our degree is odd, right? It's odd. So we know it's either going to go down and up or it's going to go up and down. And you're like, well, Dr. B, what do you mean it's going to, the end behavior, the end pieces of the graph. So we know this is what it's going to look like. And then because we know our foundational graphs, we know that, we know that this is f of x is equal to x cubed. We know that x cubed looks like an s. So that's what I'm going to keep in mind. Why? Because my picture over here has x cubed. So I know it's going to be similar to x cubed. Because it's odd and because the leading coefficient is positive and it's x cubed, it's going to be the opposite signs, right? Good. So let me see. Get my black. So that means it's going to be this one, right? So it's going to go down. That end of the graph is going to go down, and then that end of the graph is going to go up. Now you're like, I don't know. You can always do a t-table. You can always do a t-table. And what I try to do, you say, okay, well, if x is -1, you're still going to come out with a negative, and so it's going to be down, right? See, this is what we wrote. Good. We're good, right? Yeah. So see how it's going down? The end behavior is here. It's going down, but the end behavior on this side is up. Remember, in between, it can do any willy-nilly it wants to. The end behavior means what are the ending points of the graph. We don't know where they end, but we know that this is down and this is up. Okay? Okay, let's do another one. X minus 3 squared. Now you're like, oh, I don't know. Well, what you can do is, this means x minus 3 times x minus 3, right? So if you do the FOIL method really quick, you would get x squared minus 3x minus 3x plus 9. And then when we combine like terms, you would have x squared minus 6x plus 9. So that's what it looks like. So now, what's the leading term? Good, x squared. What's the leading coefficient? 1. What's the degree? 2. And when we know it's an even degree, we know that the end behaviors are going to go the same direction. They're either going to go both up or they're going to go both down. And because the leading coefficient is positive, we know it's going to be up, right? Or we're confident that it's going to be up. We don't know what it does in the middle, but we know that the end behavior is going to be up, right? Let's see. Perfect. I hope this is making sense. And then we took this and turned it into that so that we could see what the degree is. And remember, at any point, leave a comment if you have a question. I think I have maybe one more. Let's see. I think this might be the last one. Not for sure. Okay. Negative. I think we might have one more after this. I like to give you like a crazy one just in case you get to when you get to your work. Okay, here's a polynomial function. This is a valid polynomial function. What is the leading term? No. Why? Because they didn't write it. They didn't write it in the order we normally see it in, right? If I were to rewrite this in descending power order, it would be negative x cubed minus x squared plus 5x minus 3. You see that? We're writing it in descending power order. Or you don't have to do that. Just make sure when you pull it out, you see what you're looking at, okay? So the leading term is negative x cubed, right? You see that? So negative x cubed. The leading coefficient, we don't write a 1, but it's an understood 1. And then what is the degree? The degree is 3. Because the degree is odd, we know that the end behaviors are going to be opposite. So it's either going to look like that, or it's going to go, the end behavior is going to be down and it's going to be up. Now this is negative, so it's going to be the opposite of x cubed, right? And I'm thinking, why are we thinking x cubed? Because it has an x cubed on it. We know that x cubed looks like this. When we say f of x is equal to x cubed, we know it looks like that. So if this is a negative x cubed, it's going to be the opposite, right? Where the left side is up and the right side is down. Let's hope we're right. Are y'all confident? I'm confident. Let's see. Because sometimes I forget too. Yep. Left side is up and the right side is down. Did we write that right? Yep. Negative x cubed, negative 1, 3. Yep. So that's the end behavior. And then the end behavior on this side. In the middle, it can do bloop, 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 bloop. But because you know it's an odd function, you know that the end behaviors are going to be opposite each other. See that? Cool beans. I think I have one more. Yeah. So I wanted to give you one that wasn't like so straightforward like the others, because I want you to think, how do I know what the degree is? Now, you can multiply all this out and get what the degree is, or just look at it. This is a cubed. This is to the 1 power, and this is to the 1 power, right? So you have 3 plus 1 plus 1, that's 5. So this polynomial function has a degree of 5. You can do that when it's multiplication. Now, if you're like, oh, I don't know, that doesn't make sense to me, I'm hoping it makes sense to you, because if you take this and then you have x minus 1 times x plus 5, you can multiply it out. It's a lot of work. Not a lot of work. When you FOIL this, you would get x squared plus 5x plus a negative x plus a negative 5. So that's x squared, what is that, plus 4x minus 5. And you still have to multiply it by this 2x cubed. And see, when you take 2x cubed times everything, right, you get 2x to the 5th plus 8x to the 4th minus 10x cubed. Check my math. 3 plus 2, 5. 2 times 2, 2 times 4. Yeah. And so as you can see, your leading term would be 2x to the 5. But again, you can say, okay, you have your 2, that's a 1, that's a 1, right? And you have your 3. So you have 3, 1, 1, that's 5. So it's still going to be 2x to the 5. So hopefully you remember when you see it this way, you can just add up all the x variables and put them together. Okay, sorry. So that's 2x to the fifth, right? What's the leading coefficient? The leading coefficient is 2, right? So far so good. And then what is the degree? The degree of this is 5, right? And it's odd. So we know that it's going to be what? We know that the end behaviors are going to be opposite, right? So it's going to be like that, or it's going to be like that. And because it's positive, we know it's going to be this one, right? We're confident that it's going to be this one. Why? Because I'm thinking of x cubed. F of x is equal to x cubed. Okay, I'm keeping the foundational graph in the back of my mind. Let's check ourselves. Well, look at that. We got it right. Now you see all this? Remember I told you it can do some stuff in there, but this end goes this way, and then this end goes this way. Now, if you were to put this, I only could show so much to you, but this graph is like going up, and then it's coming down. It's doing this little loop-de-loop thing, and then it's coming back up again. You just can't see that part there, but that's what it's doing, okay? And because you can't see all of it, that's why the end behavior actually helps, okay? Cool beans. 0 of polynomial functions. Now you're like, what? So on all the graphs that we saw before, if you noticed, a lot of them were crossing the x-axis and going up and flipping, or some of them were like with the x squared, it was touching the x-axis and turning and going up. Well, wherever the graph hits the x-axis, wherever the graph hits the x-axis, those are called zeros, or sometimes you'll see the word roots and solutions. Okay, you'll see the words roots or solutions. But the zeros of the polynomial functions, real zeros, and I guess I should have put here real zeros, because you don't want imaginary or complex. You can't even see that. So real zeros, I put it here, good. That's where it actually hits the x-axis. Now, the zeros can tell you so much, but right now we're just going to talk about the zeros, and then we'll talk about the multiplicity of zeros, because the zeros tell you where it's going to touch the x-axis, and it's either going to slice right through or it's going to turn around. That's where you use the multiplicities. But what I want you to get out of this is that each zero, each real zero, real root, real solution is an x-intercept. Now, the x-intercept is where the graph crosses the x-axis. Those are x-intercept points. Okay, let me say it again. These zeros, where the graph of the function actually touches the x-axis, it'll be where the y, remember this is the same thing as y is equal to 0. They're also x-intercepts because they tell you where the graph crosses at the x-axis. It's either going to cross at that point or it's going to touch it and turn around. But those are all zeros. And how do you find the zeros? You just use factoring. You use factoring. The factoring will tell you where all the zeros are. Not all zeros are real zeros, okay? Real meaning real numbers. You can have some imaginary zeros. You can have some complex zeros. You can have, we'll just stick with complex. So you either can have real zeros or you can have complex, or what they call imaginary zeros, okay? But in this lesson, we're just going to stick with real zeros, okay? The ones that you see on the x-axis that you can see, not the fake, not the imaginary ones, not the fake ones, okay? Multiplicity of zeros. So these go hand in hand. You get your zeros, but then multiplicity of zeros. And you're like, well, Dr. B, what does multiplicity means? What I mean by multiplicity is how many times, how often does that zero show up? So if you have a polynomial function and you factor it and you get all the zeros, how many times does each zero show up? Because that's going to tell you some more details about the graph. If the multiplicity of the zero, if it's an even multiplicity, meaning if you have, like, if the zero shows up 2 times, if it shows up 4 times, if it shows up 6 times, if it shows up 8 times, that means it's going to touch that zero, that point, that x-intercept is going to touch it, and then it's going to turn around. Remember when we did the graph of f of x equals x squared? It touched right here and then it turned around because it had, that 0 had an even multiplicity. And I will show you what that looks like. I'll give you some examples. Now, if your 0 has an odd multiplicity, it's going to cross straight through the x-axis. So you remember when we had the graph of x cubed? When it's crossing, see, it's crossing directly through the x-axis. And I drew it like that, but you could have a graph that goes just like this. You could have a parabola that goes like this, where it crosses. Wherever it crosses the x-axis, remember, those are x-intercepts. Those zeros are real zeros. They're real numbers, and they cross the x-axis if they have odd multiplicity, meaning the 0 showed up once. It either showed up 3 times, 5 times, 7 times, 9 times, all your odd values. It crosses the x-axis. If it has even multiplicity, it touches the x-axis at that x-intercept, and then it turns around. Whether it turns around and goes up or it turns around and it goes down. Okay, cool beans. So let's do a couple of examples so that you can see how to find the zeros and then what it means by multiplicity. I promise you it's very simple. And again, we're going through all of this because when you see it, it'll help. When you see this, you're going to be like, oh, it has a cubic. I know what a cubic function looks like. The end behaviors are opposite, right? I know that. So that one thing I know now is the end behaviors. Now I need to know, well, where does the graph cross the x-axis? Can you find the x-intercepts and the y-intercepts? Absolutely. Absolutely. This is the same concept what we're doing here. It's just if you can find all the zeros and then know how many times how many times that 0 appears. If it appears at an even number of times, it's going to touch that 0, that x-intercept, and it's going to turn around, whether up and down or left or top to bottom or bottom up. And then if it has an odd number of times, it's going to slide straight through that x-intercept. So first, what you want to do, you want to use factoring. Now we have this polynomial function here. How do you factor this? Now, I did do a video on factoring techniques. I will make sure that I put it in the description because I want to make sure that you know how to factor. You want to make sure you understand what a polynomial is and how to factor before you even jump into this lesson. And I have 2 videos for those, okay? Okay, so before I factor this, I need to figure out what I need to put together, right? Yeah. Let me rewrite this. Okay, so I'm going to put, x cubed plus 2x squared minus 4x minus 8. I just rewrote what I want to rewrite is this part. I'm going to attach the minus to the numbers, okay? So this is what I'm going to do. X cubed plus 2x squared plus a minus 4x plus a minus 8. Y'all see that? I just moved the minuses next to the numbers and I put plus in between. Now I'm going to factor by grouping. You're like, Dr. B, what does that mean? I'm going to group these 2 together and I'm going to group those 2 together. Okay, so when I do that, what can I factor out on this side? Well, I can take out an x squared, but I can't take out any numbers, right? So then I'm going to factor out an x squared, and when I factor out an x squared, I'm left with, what is that? I'm left with x plus 2. You'll see that? X squared times x is x cubed, and x squared times 2 is 2x squared. Then I'm going to say plus. When I factor on this side, what can I factor out? Well, we have minus 4 and we have minus 8. The common factors between minus 4 and minus 8 is going to be a minus 2, right? So this is going to be a plus minus 2. And this is going to be 2x plus 4. Let's check our math. A minus 2 times a 2x gives me a minus 4x. That's good. And a minus 2 times 4 gives me a minus 8. Y'all see that? Y'all see that? Now, did I factor out the right number? Now, I'm doing this because I don't want you to just follow what I'm doing. I want you to think, what should I have factored out? The greatest common factor. Yes, 2 is a factor, but is it the greatest common factor? No. Good job. And if you do that, don't worry. You just keep factoring until you can't factor anymore. I should have factored out a -4. Why? Because that's the greatest common factor between them. And when you do factor by grouping, when you do that, you want your two inner pieces to look the same. You want this piece to look like that piece. That's another giveaway, right? That's why I looked at it. I'm like, that ain't right. So -4 times x gives me the -4x, and then the -4 times the 2 gives me the -8. Now that I've factored that out, now I can pull these two x plus 2's. I can factor them out and pull them to the beginning, like the distributive property. So then I have x plus 2 that I factor out to the beginning, and then I'm left with x squared minus 4, right? Am I done? Nope, because I can continue factoring. Do you recognize this? This is a difference of what? A difference of squares. Good. This is a difference of squares. So then if you remember your difference of squares, let me write down what I did. So here I'm going to put, I did factor by grouping. Just so you can, when you go back and you're writing your notes, we did factor by grouping. And here we're going to do, we're going to factor, I'm going to say difference of squares. Make sure I have room. Okay, difference of squares. So this is the difference of squares. And our difference of squares formula tells us that we can write this as, wrote that as a different color. We have x plus 2, and then this will be x plus 2 times x minus 2. And all of this we're going to set equal to 0. So once we, I don't know where that came from. Once we get down here, we're going to set it equal to 0, okay? So we get it, once we set it equal to 0, then when you write it, this becomes x plus 2 is equal to 0, x plus 2 is equal to 0, and then x minus 2 is equal to 0. Because we're looking for all the x-intercepts. The x-intercepts are the x values that when you plug in x, you get y equals 0, or you get f of x equals 0. So wherever f of x is equal to 0, those are my x-intercepts. Those are my real zeros. Those are my roots. Those are my solutions, okay? And I'm saying it in all the different terminologies that you'll hear it say. So now when I solve for this, right, I'm going to subtract 2. So I'm going to subtract 2, subtract 2, subtract 2, subtract 2, and I'm going to add 2 here, add 2 here, and those will cancel out, right? So I'm left with, can y'all see that? Yep, x equals, what is that, -2, x equals -2, and then x equals 2. These are all my zeros. Y'all see that? I have 3 zeros. You see that? I have 3 zeros, or technically these are the same. Sorry. Technically these are the same, right? But you still have 3 zeros. And that's the cool thing about the degree, because it should give you a hint as to how many zeros that you have. So these are my zeros. Okay. That one, and that one. So I have 3 zeros. Now, the -2 did appear twice, right? So then let's talk about multiplicity. Do I do that yet? No? Okay. We'll get to that. I'm going to show you. So the zeros for that particular function, our zeros are -x, wow, -2 and 2, right? We found those. And then that means that I have x-intercepts at x equals -2 and x equals 2. Why are they x-intercepts? Because when I set them equal to 0, I found the x values. To find x-intercepts, you set y equal to 0 and solve for x. Remember, this is what we're doing. We're saying f of x is equal to 0. And we're saying find all the x values where they give you 0. That's what we're doing here. Okay, so these are my 2 zeros, -2 and 2. That means I have x-intercepts at x equals -2 and x equals 2. If you look really close at this graph, that is -2 and that's 2. So this is x equals 2 and this is x equals -2. Okay, now the graph passes through these 2 points. Now I'm saying passes through. I should have said the graph touches or passes through these 2 points. So you pass through here and we pass through here. Remember when we were talking about multiplicity? The multiplicity of zeros tells you whether you touch that 0 and turn around or if you cross straight through it. So let's look at the multiplicities. So these were our zeros, right? -2 has a multiplicity of, has an even multiplicity. Why? Because it showed up 2 times. Let me go back. See, -2 showed up twice. That's an even multiplicity, and 2 showed up once. So then it has an even multiplicity. So that means at x equals -2, the graph is going to touch it and turn around. Now, how did we know that this was the end behavior of the graph? Well, because the leading coefficient is 1, it's positive. It has an odd degree, so that means the end behaviors are going to be opposite each other. And we know that when it's positive, when the leading coefficient is positive, it looks like that. So we know it's going to reach that 0 and it's going to turn around because it has an even multiplicity. And then 2 only showed up once, right? 2 only showed up once. So that means when it gets to x equals 2, it's going to cross straight through. See how that works? So even though you can graph these with x-intercepts and y-intercepts, if you know the end behavior, if the end behaviors are opposite or going the same direction, and then if you can find all of your zeros and then say, how many times does this 0 show up? What's the multiplicity of it? Then I'm going to know, does it touch the graph and turn around, or does it cut straight through? Okay? All right. Stay with me. Let's do another one. Let's look at this one. Now, this one's broken down for us, right? We don't have no factor by grouping, nothing. If I were to rewrite this, it would be 2 times, what is that? X minus 5, and then x plus 4 squared. That just means this. That means you duplicate it that many times, right? And you set it equal to 0. Well, obviously, we can't set 2 equal to 0 because 2 is not equal to 0. So you just kind of throw that out. But then you have x minus 5 is equal to 0, or x plus 4 is equal to 0, or x plus 4 is equal to 0. And you're like, well, how do you do that? Because that's how, when you factor, you can set each of those factors equal to 0. So now let's solve for x. So I'm going to add 5 on both sides. I'm going to subtract 4 on both sides. And then I'm going to subtract 4 on both sides. Because when you, whatever you do to one side, you have to do to the other side. These cancel each other. And so here I'm left with x is equal to 5, or x is equal to -4, or x is equal to -4. I hope y'all notice what we're doing. We're literally solving these equations. We're solving for the equation. And when you come up with something like this, you can set x equal to 5, x equal to -4, x equal to, you can set each of these factors equal to 0, and then you solve for them. So what's the multiplicity? What's the multiplicity on 5? It has a multiplicity of 1, right? So this is of 1. Or you know what? Let me not put numbers because I don't want you to be. So this has an odd. Why? Because it only showed up 1 time. What about the multiplicities on -4? It has an even multiplicity. Why? Because it showed up twice, and 2 is an even number. Y'all see how that works? So just remember that. Don't forget that, okay? Just remember that. Whoa. Okay, we're good. Just remember that, okay? 5 has an odd multiplicity. Because it's odd, that means it's going to cross straight through that intercept. And then x equals -4 has an even multiplicity. So that means the graph is going to touch that 0 and turn around. All right. The zeros were -4 and 5, right? That's what we said when we solved for that. The graph has x-intercepts at x equals -4 and x equals 5. One of the things I want you to notice, I'm always listing the negative numbers first and then the positive numbers second. Because when you read graphs, you normally read them from left to right. And so your negative numbers always come first, and then 0, and then your positive numbers. So you're always going to see me try to write the negative numbers first and then the positive numbers. So the zeros, the roots, the x-intercepts, the real zeros, the real zeros, because they're real numbers, of f are -4, which is here, and 5. Okay, so this is the point x equals -4, and this is the point x equals 5. These are x-intercepts because that's where they cross or touch the x-axis. That's where y is equal to 0. This is the point -4, 0, and this is the point 5, 0. Y'all see that? So the graph has x-intercepts at x equals -4, x equals 5, and passes through these points. Now, the reason why I'm showing you 3 different ways to write it, because I don't want you to get confused. They all represent the same thing, okay? They all represent the same thing. The zeros are the x-intercepts, okay? The x-intercepts, if you write them like this, that's just writing them as equations. So if they say write your answer as an equation, this is what they're talking about. If they say list your zeros, just put the numbers. If they say write your answer as an ordered pair, just write it as an ordered pair. But do know all 3 of these represent the same thing. So that's why I'm writing it this way. Now, we said that the 5 had a multiplicity of 1. So that means the graph is going to cross straight through it, which it does, right? And then we said the -4 showed up 2 times. So it had an even multiplicity. So that means the graph is going to touch it and turn around at that 0, at that intercept. Now, how did we know that the graph, the end behavior was this way and this way? Because if you multiply all this out, you do get, that's 1, right? And then this ends up being an x squared, so you have a degree of 3. So this is actually an x cubed. It's a positive x cubed. So I know that's my end behavior and that's my end behavior. See, it all works out. It all works out together. Multiplicities. We said the zeros were -4 and 5, right? -4 had an even multiplicity. So like we said, it touches and turns. Good. And then 5 had an odd multiplicity. So that means it's going to slice straight through that 0. The 0, the x-intercept, the root, the solution, however you want to call it. Okay. Remember, at any point, you can leave a question in the comments. All right. Cool beans. Let's look at this one. Got 4 spots. What's the first thing we're thinking about? Yep. Factor by grouping. Okay. Factor by grouping. That's the first thing we're thinking about. So let me rewrite it. So I have x cubed plus 5x squared. I'm going to put plus minus 9x and then plus a minus 45. All I'm doing is taking the minus and I'm attaching it to the numbers. Okay. So now I'm going to group. I'm going to group these 2 together. And then I'm going to group these 2 together. A lot of times factor by grouping works the way they're laid out. If not, you just rearrange the numbers, okay? So what can I factor out on this left-hand side? Looks like I can factor out an x squared. And when I factor out an x squared, I'm left with x plus 5. Y'all see that? So I am hoping that this other side over here is also x plus 5, right? And it looks like it's going to work out. I can factor out a -9. And when you do that, a -9 times x is the minus 9x. And then a -9 times 5 is the minus 45. See how that works? So it worked out in our favor. So now I can take the x plus 5 and I can pull it out to the front because that's how factor by grouping works. Let me put here that we did factor by grouping in case you're writing this in your notes. Factor by grouping. So then we factor out the x plus 5. And then we're left with x squared minus 9. See? Now, what do you notice? Yep, this is a difference of squares. And you're saying, Dr. B, what's a difference of squares? Do y'all see it? This is a difference of squares. Okay, not this. That's done. That's gone as far as it can go. This is a difference of squares. This is x plus 3 times x minus 3. So if I rewrite this whole thing, I have x plus 5 times x plus 3 times x minus 3. And we're going to set that equal to 0. And then now we can put all of our x plus 5 is equal to 0, or x plus 3 is equal to 0, or x minus 3 is equal to 0. Now we say or because you want to make sure that these zeros work. That's a totally different lesson, okay? So right now we're just assuming that all of these zeros work, okay? Totally different lesson. Now when I solve these for x, so we can get our x-intercepts, whatever I do to one side, I have to do to the other side. Plus 5, negative 5, plus 3, negative 3, negative 3 plus 3, they cancel out. So I have, can I write there? Yep, x equals negative 5, or, I'm going to write over my name, x equals negative 3, or x equals 3. These are my zeros. These are my x-intercepts. These are my roots to the polynomial function. Now, what do you notice about each of these zeros? How many times do they appear? Good. Once. So that means negative 5. That 0 has an odd multiplicity, so it's going to cross straight through. X equals negative 3 appears only once, so it has an odd multiplicity, so it's going to cross straight through there. Our graph is going to cross straight through there. And then x equals 3 has an odd multiplicity because it only shows up once, and it's going to cross through the graph there. My leading term is x cubed. My leading coefficient is 1. And my degree is odd. So I know that this graph is going to have an end behavior, sort of like that. I don't know what it's going to do in the middle, but I know the end behaviors are going to be opposite each other. Let's check it out. Remember, each 0 had an odd multiplicity. Cool. And it looks exactly like that. See the end behavior? That's the far outside of the graph. And then this is the far inner part of the graph. You see that? See that? That's the end behavior. And then my zeros are negative 5, negative 3, and 3. Y'all see that? And it crosses because the multiplicities were 1, right? Good. So remember, all three of these represent the same thing. I'm saying them 3 different ways so that you can get in your mind they're the same thing. So my zeros are at x equals negative 5, x equals negative 3, and x equals 3. My x-intercepts are at x equals negative 5, x equals negative 3, x equals 3. The graph passes through the point negative 5, 0, negative 3, 0, and 3, 0. Y'all see, it's the same thing, just different ways to say it. If they say list your zeros, you list them. If they say write them as equations, you write them as x equals whatever. If they say write them as ordered pairs, you write them as ordered pairs. Okay? And notice that I'm listing my negative ones first and my positive ones last because you normally read graphs from left to right. So let's check the multiplicities. Yep. Negative 5 only showed up once, so it has an odd multiplicity. Negative 3 only showed up once, so it has an odd multiplicity. And then 3 showed up once, so it has an odd multiplicity. So when you draw the graph, it's going to slash through each of those zeros. It's not going to touch and turn because they have odd multiplicity. They're going to cross straight through. Cool beans? All right, let's look at this one. And y'all are probably like, Lord, don't let it get you down. Take each piece and let's rewrite it. Not rewrite it, but we're going to set it equal to 0. Remember, this just means it duplicates that many times. It duplicates 2 times, it duplicates 3 times. So if I were to rewrite this, it would be negative 4, and then you'd have x plus 1/2, and then another x plus 1/2 because it had 2 of them, right? And then this one is 3 times. And set that equal to 0. Okay, so that's what that means. Set that equal to 0, and then of course negative 4 cannot be equal to 0, so that drops off. But when you solve for the rest of these, you have x plus 1/2 equals 0, or x plus 1/2 equals 0, or x minus 5 equals 0, or x minus 5 equals 0, or x minus 5 equals 0. Y'all get the gist, right? And when we solve this for x, we're going to subtract 1/2 on both sides. Same thing here. Subtract 1/2 on both sides. This one we're going to add 5 on both sides. Add 5, and we're going to add 5, add 5. Okay, it's getting kind of sloppy, ain't it? So anyway, so this is x is negative 1/2, x negative 1/2, x equals 5, x equals 5, x equals 5. Y'all see that? So or. The same way I'm moving through these is the same way you want to move to those. So the 1/2 it shows up twice, right? So it has even multiplicity. That means at x equals -1/2, it's going to touch and turn, whether it's this way touch and turn or this way touch and turn, okay? And then x equals 5, they have odd multiplicity, right? So it's going to cross straight through. Let's check. Let's see if we're right. Okay. Woo! Now, I didn't have a lot of room to give y'all the whole graph, but this part here is almost like a parabola a little bit, and then it goes up and then it comes down. But this up was way up there, like way up there, okay? So that's what I'm saying. Sometimes you can't see the whole graph, and that's why if you kind of know these concepts, you know, okay, it's gonna go up, da da da. Now, woo, let me show you. This, when we squared, let me go back one. When we squared this, see you have 1, 2, 3, 4, 5. So it's going to be like an x to the 5th. This is your leading number, so it's really going to be a -4 x to the 5th, and it's going to have a whole bunch of other stuff. But we know it's odd, so we know it's going to be what do you call it? The end behaviors are going to be opposite. It's minus, so that means this leg right here, I know you can't see, it's probably up like that. And then this end part right here is down. So the end behaviors are opposite. We have zeros that f equals, trust me, this is -1/2. See how it's real close to that 0? And then this right here is x equals 5, okay? So those are my zeros. Notice at the 1/2, it touched and turned because it had an even multiplicity. And then at the x equals 5, it went straight through it, okay? These all represent the same things. Listing them, equations, ordered pairs, okay? Go to multiplicities. Yeah, it showed up twice. So it's going to touch and turn. Showed up 3 times. So it's going to cross straight through. I hope this is making sense. I hope this is making sense and that you're feeling good about it, okay? Couple more things. Okay, just a couple more things to help you figure out where the zeros are. The existence of real zeros, not imaginary zeros, real zeros. The real numbers that we talked about at the very beginning. They have this intermediate value theorem, and I'm just going to read this to you, okay? It says, let f be a polynomial function with real coefficients, meaning real numbers, okay? If f of a and f of b have opposite signs, there is at least one x-intercept at x equals c between x equals a and x equals b such that f of c equals 0. What? I know. What you're doing is, what they're saying is, remember your f of whatever, that represents your y-axis. And they're saying that if you have a y at a point x equals a and you have a y at a point x equals b, and they have opposite signs, meaning one y is positive and one y is negative, what they're saying is you've had to have crossed the x-axis. You had to have crossed it somewhere. There's an x-intercept in between those 2 points if your y changes. So you're basically comparing the signs. And I put this little photography here to remind me to show you a picture. Let me show you a picture of what I'm talking about. So let's look at this. Can I blow this up? Yeah, I'm going to blow that up right there just so you can see it. Here's what I'm talking about. This is your y-axis, right? Yes, this is your x-axis. And when you're talking about functions, y is the same thing as f of x, okay? So let's just say that. They're saying if you have an f of a and an f of b that have opposite signs. Let me show you. So if this is my x-axis, I'm going to say this is my a point and this is my b point. Because your x-axis, you have all these numbers, right? And if I pick a point up here, on the y-axis, let's say here, and then I'm gonna pick a point right here. So if I pick this point here, this is the point a, f of a. Do you agree? Let me write. Can y'all see? Okay, good. You can see. I wanted to make sure you could see that. This is the point A, the x value, and then f at A, right? Which is the y value. Do y'all see that? This point right here. Okay, so this is your f. This is your f of x, your y-axis, right? And I'm saying the point here is a f of A. And then this point here, this point here, see where this is the point on the y-axis here, and then this is the point on the y-axis too. So this is your y-axis, okay? This is your x-axis. Do you agree that this is the point B, f at B? Whatever the number is, do you agree that's this point here? In fact, let me put that point. Yeah. So your polynomial, basically the intermediate value theorem says there exists, if I'm going, however I draw it, let me draw it. If I'm doing something like this and I'm coming up and I'm coming through here, what they're saying is there has to be a point here that you cross, and they're calling that point C. They're saying that you had to have crossed the x-axis in order for the y sign to change, because these down here, these are your negative y values, and these are your positive y's. You'll see that? So they're saying is if you compare, if you pick 2 points on the x-axis, and when you plug it into your function, if one comes out negative and then one y value comes out positive, they're saying you had to have crossed the x-axis, because the only way to get from a negative y to a positive y is to go up or to come down, right? To go from a positive y to a negative y, or a negative y to a positive y. You see what I'm saying? If you go up, you've crossed the x-axis. If you go down, you cross the x-axis. The only way that these y values are going to change is if you cross the x-axis. That's all the intermediate value theorem is saying. If you compare 2 points, if you have 2 points and you notice that this point gave me a positive y value and a different point gave me a different point on the x-axis gave me a negative y value, I crossed the x-axis somewhere. I don't know where. That's what all those other things will tell me, but that means I crossed the x-axis. So let's look at an example. This says, show that f of x, 3x cubed minus 10x plus 9, has a real zero between x equals -3 and x equals 2. Has a real zero between x equals -3 and x equals 2. If it has a real zero between x equals -3 and x equals -2, that means the sign of the y's are going to change. If the sign of the y changes, that means we have crossed the x-axis somewhere. Going back to this, if you go from a negative x to a negative y to a positive y, you have to cross the x-axis to get there. That's all we're saying. And if the sign changes on the y, that means you've crossed the x-axis. So what you do here, essentially just take... find f at -3 and then find f at -2. Remember, y is the same thing as f of x. Y is the same thing as f of x. Y is the same thing as f of x. So that's going to be 3. Let me do it like this. So that's going to be 3 times that cubed minus 10 times that plus 9. And let me write it here. So we're going to plug in -3, and we're going to plug in on this one -2. Yeah, -2. So now let's see what we get, right? So that's going to be what? 3 times, what is that, -27? And you're like, Dr. B, how did you get that? -3 times, so -3 times -3 is a positive 9, but you have one more 3 because it's cubed, okay? And then that's going to be, equal, or no, we're doing minus. So a minus 10 times a minus 3, that's going to be a positive 30. Y'all see that? And then plus 9. So let's stop there, because I'm probably running out of room. Okay. And then so we have, if you put this in your calculator, you should get minus 81 plus 30 plus 9. And when you put that in your calculator, make sure you can still see that, you end up with negative 42. Okay. Now, f of negative 2, you get negative 2 cubed. That's going to be what? A negative 8, right? Because negative 2 times negative 2 is a positive 4. 4 times negative 2 is a negative 8. So we're going to have 3 times negative 8, right? And then that's going to be plus, what is that, a positive 20? Because a negative 10 times a negative 2 is going to be a positive 20. And you're like, where did you see that? Right here. And then plus 9. Ooh. Okay, make sure y'all can see that. So then 8 times 3, that's going to be what? A negative 24, right? So we have negative 24 plus 20 plus 9. And when you put that in your calculator, you get 5. So essentially what they're saying is from x equals negative 2 to x equals negative 3. If I can draw a little, can I make this? I don't think I can. I'm just going to draw a little graph here just so you can see it. Okay, so x equals negative 2 is here. X equals negative 3 is here. Do you agree with that? This is the x-axis, and this is the y-axis. You know what? Let me get a scratch paper because I really want you to see this. Okay, scratch paper. So at x equals negative 3, we found that f of negative 3 was negative 2. And then at x equals negative 2, we found that f of negative 2 was equal to 5. If I were to write this as an ordered pair, this is negative 2, negative 42. That's my x and my y. And then this is negative 2 and 5. Okay, got my little graph. So, and this is guesstimating because we don't have enough numbers. But you have your x-axis and you have your y-axis, right? If there's a real zero that exists between these 2 points here, then the y value sign changes. See how the y value sign changes? But I want you to see it. I'm visual, so I want to see it. X equals negative 3 is right here, and y equals negative 42. That's going to be somewhere down here, right? So I'm just gonna mark right here. Okay, I'm gonna say negative 3, negative 42. Okay, and then the other point is negative 2, 5. So when x is negative 2, y is 5. That's somewhere right here. You see what I'm saying? In order to get from this point to this, you have to cross the x-axis. So that means because you cross the x-axis, there has to be an x-intercept. And if there's an x-intercept, you have a real zero, meaning it's a real number. It's not an imaginary number. That's what the intermediate value theorem says. If you can go from one point to another point, and if your y values change signs, that means you went from a negative y to a positive y. Because the only way you can get from this point to this point is to what? Cross the x-axis. I don't care if you loop-de-loop, and get through, you still got to cross the x-axis. Does that make sense? I hope that makes sense. If not, leave me a comment and we can do some more of those. Okay, turning points. Just one more thing. I know you're like, oh my God, one more thing. So turning points on a graph, that's just where the graph changes direction. When it comes down and goes up or comes down, or when it goes up and it goes up, comes back down and goes back up, like on x cubed. That's what that means. So you basically look at the degree of n. So if the degree of n is 3, you only can have at most 2 turning points, meaning you can have 0, 1, or 2 turning points, meaning the graph is not going to turn 3 times. It only can turn at most 2 times, n minus 1. And wherever it turns, you have a relative maximum or a relative minimum. Now, I put this disclaimer down here. Be grateful. So if you don't have a graphing utility or you know some calculus, sometimes it's very hard or difficult to know where the graph actually turns. but this just helps you to know that it turns somewhere. There's one of the graphs we did that an example. I think the maximum was like at y equals 550. Well, we ain't got time for that. So just know it turns, okay? So this just only thing you need to know from here is how many turning points can you possibly have. You look at the degree of the polynomial and you say, I can have at most n minus 1. So just real quick, and I put thanks goodness because we ain't got time for calculus, none of that, right? We're in algebra. All right, so look, if you're looking at x squared, it can have at most one turning point, at most 1, because n minus 1 would be 1. And if you look, it does have exactly 1. So it either can have 0 or 1. And then when you're looking at x cubed, it can have at most 2 turning points. And you see it turns here and it turns here. 2 turning points. But it can't have more than 2. Okay? Easy peasy. Easy peasy. I know y'all are done. So some common mistakes. Not knowing what the foundational graphs looks like. Make sure you know what x squared looks like. And for this one, really x squared and x cubed, make sure you know what they look like. Because if you know what they look like, it's going to help you figure out what the other graphs look like. If you have an odd degree, it's going to follow a pattern of x cubed. If you have an even degree, it's going to follow a pattern of x squared, which is the parabola. You just have to know, does it go up? Does it go down? Are the signs opposite? If it's an odd degree, opposite signs, even degree, same signs. Don't think that anything with an x is a polynomial. Remember, it has to fit the definition. You can't have fractions in the exponents. You can't have negative exponents. You understand what I'm saying? And your coefficients have to be real. Everything has to be a real number. You can't have imaginary numbers, okay? Misidentifying the degree. If they don't put it in descending order, sometimes you're like, oh, the first one. It's not the first one. It's the term with the variable that has the highest degree, okay? Don't ignore the leading coefficients. That helps you know if the end behaviors are up or down. Okay, don't forget about that. And then multiplicity. Multiplicity means how many times does the 0 show up? Multiplicity. How many times does it show up? Multiplicity. Okay, and always check behind yourself. Key takeaways: no negative exponents, no fractions, no variables in the denominator. Okay. The highest exponent determines the degree, not the first term that you see. The highest exponent determines the degree, okay? Know the shapes and behaviors of the basic graphs. In this particular lesson, x squared and x cubed. Remember, real zeros, the real zeros, meaning they're real numbers. They're also called roots. They're also called solutions. They're also called x-intercepts. If they're real, not imaginary. Real numbers, the roots, the solutions, the x-intercepts. And always double check your work. Now, you should be able to complete your assignment with success. Remember, some questions on your homework may be harder or easier than the ones that we did in this assignment, in this lesson. Be sure to follow the steps step by step, because you keep doing the same things over and over again. Each question should work out. Not saying you won't meet any tricky ones. You might. Remember, at any point during my videos, you can reach out to me, leave your questions in the comments. I am always happy to help. All right, y'all. Thanks again for another good lesson. See y'all later. Bye.